Excuse me. Excuse me. So maybe you can draw this. Okay, so this is a very high level diagram of how a computer looks like, right? So you can identify certain components when you look at a computer. For example, you can identify memory, right? Memory is the place where you store your data and your instructions as well. And then you have something called as input devices, something called as output devices, right? So your screens go here, your mouse and keyboard go here. And one of the major components is what is called as the processor. Some people also call it as the instruction set processor because it executes instructions, right? So this is also called as a microprocessor or an instruction set processor, or some people just call it as the processor. Some people also call it as the CPU or central processing unit. Different names for the same thing. Anyway, so what does the processor contains? Well, it contains one or more ALUs and it contains a couple of registers. Registers are used for temporary storage. And there is something called as a control unit, which is like controlling all the components inside a processor. So a processor has many more components I have not shown here. And then there are one or two buses which interconnect these so that you can actually transfer something from the register to another register, from a register to an ALU, and so on. You can do all that, right? So this is what really happens. Yeah. So when we talk of, so you might have heard of something called as clock speed, right? So clock speed essentially refers to the speed of the clock within the processor. So what we are saying is, so there are a couple of things to understand. The first thing to understand is that this circuit inside the processor is clogged, right? Okay, so can somebody tell me why do you want a clogged circuit? Why do we have clogged circuit? Can somebody tell me why do we have clogged circuits? You have you've done some course on digital circuits, right? To allow for delay. Okay, so you want a clogged circuit to allow for delay. No, but what is the need for a clogged circuit? Why do you want things to be clogged? To time all operations. Do you mean to say synchronize? Okay, right. So yeah, so somebody said that. So typically what happens is that if you look, there are two reasons for it. The first reason is that if you have a clogged circuit, everybody is supposed to respond on clock edges, right? Or clock levels, depending on the what type of clock it is, triggering it is. Anyway, so the first thing is everybody can synchronize. So, for example, if one body is faster, the other is slower, then if the clock is wide enough, everybody can synchronize. That is one. And the other reason is it allows the circuit design to be simple, right? It allows the circuit design to be simple, right? So you can, and it can be faster as well. So a couple of reasons why you would want a clock. Anyway, so when we refer to clock speed, we are referring to this clock, the clock on the internal processor bus, right? Generally what happens is, if you see here, I have shown just one bus connecting everybody, but usually it is not like that. So you will actually have, so this part that you see here, there will be a bus which interconnects the processor and the memory, and this is called as the memory bus, right? So you would have this. So you probably not have something like this, right? So you don't have something like this. And then there could be another bus which connects the processor to the input and output. Then you can call it as the IO bus. This is what usually happens. So why don't you want a same bus for both the processor and the memory and IO devices? Because memory is faster than IO devices usually. So this memory bus is faster, this IO bus is slower, right? And this processor bus, which is internal to the processor, is the fastest because all these components are fairly fast. The registers, the ALU, and the control unit are very fast, right? So that is one thing, right? So okay, so we understand. So let me write it here. Okay, so we understand the need for clocking, right? So we said the need for clocking is one is speed, the second is simplicity of design, and the third is synchronization, right? So these are the needs. Can somebody tell me what decides the width of the clock? When I say the width of the clock, I mean the speed of the clock. Can somebody tell me what decides the width of the clock? How much should it be? Time to run the smallest possible instruction, the speed of the components, okay? Okay, very good, very good. So I see a lot of good answers. So Omkar had posed the question. Manideep says that. Sarang says speed of the components. Prabhav says depends on propagation delay of internet drops, frequency of transistors. Well, I would take the answer as the fastest does it make sense? See if you see if it makes sense to you. Can I see a couple of yeses or nos in the chat? So the bus would either be used. So the bus is mainly used for transfers, right? The bus is mainly used for transfers, or you compute something and store it somewhere and so on. So suppose the bus you use it for 100 different operations. Then the bus is supposed to be in which bigger transfers or larger operations happen in multiples of clock time. Does it make sense? Okay, what is meant by an atomic operation? An atomic operation means an indivisible operation. So either it completes or it doesn't complete. So for example, if you say you are trying to so atomic means an indivisible operation. Either it happens or it doesn't happen. Is it fine? So if you observe here, yeah. So if you observe here, the fastest operation would finish in one cycle. So fastest operation running burst takes one clock cycle. Right. So the fastest or the smallest atomic operation or a transfer on the bus takes one clock cycle. Is that okay? So what is so how does a computer operate? How does a computer keeps on repeating the fetch and execute cycle uh, for each. It means that if you remember, so question. So what determines how fast the smallest operation will take place? Okay. Okay, that's a difficult question. Uh, okay, so the smallest one, the one uh, happens fast enough. The question now the then the to get stabilized. Then there is so I know it is a little confusing right now. Okay, so that is the reason why I'm trying to keep it a little simple, right? So what am I saying? How does the computer operate? Well, if you look at every instruction of the program that you have to execute, for every instruction you do two things. One is called as fetch, the other is called as execute. Fetch essentially means you fetch from memory to the processor, and then when you fetch it into the processor, you decode the instruction, and then you execute. So whatever it needs to take to execute the instruction, you go ahead and execute, right? There are a couple of things to observe here. The first thing to observe is each instruction requires different number of cycles to execute. And when I say fetch and execute phases. So this is a combined thing that I'm saying. So what I'm trying to say, just as an example, suppose I talk of an add instruction. It could be taking 4 cycles to execute. I talk of a move instruction, it could be just taking 2 cycles. If I talk of a multiply instruction, it could be taking 100 cycles. Now, depending on the the use, right? So different instructions require a different number of cycles. That is one thing. Some instructions require both processor cycles. When I say processor cycles, I mean cycles of the processor bus, internal bus. So require both processor cycles and memory cycles. Right? Memory cycles means that you have to do transfers on the memory bus. And if you remember, the memory bus is slower than the processor bus. So I can talk of a parameter. Okay, so I just do an observation here, maybe define the parameter later on. So I can just do an observation that memory cycle time is greater than processor cycle time. In fact, this memory bus would be like maybe order of hundreds or even more slower than the processor, right? The processor cycle time is the fastest, right? So processor cycle time is the fastest time. Okay, so if we understand all this, right? If we understand all this, let me see the time. Okay, is the CR there in the class?
Yes, sir. Yes.
So just remind me, can you just remind me at 3:45 to stop? I have some work. And the other thing is I will not be able to engage the class on Tuesday because I have the whole day I am busy with some interviews. So can I hold a class in lieu of the class on Tuesday on Monday? So Monday, I think you don't have a class at 3 o'clock, right?
Sir, I'll let you know on WhatsApp.
Yeah. So yeah, you let me know on WhatsApp. So Tuesday I will not be engaging the class, right? So if it is possible, I will hold it. Otherwise, on some other day. Otherwise, you will see later on, right? So you, depending on your comfort, you let me know.
Yes, sir.
Right. Yeah. Okay. Thank you. So okay. So with this background, now what do I want to do? We want to assess the performance, right, of a computer. So I can say assess the performance. So this is my intention. We want to assess the performance of a computer. Okay, so there are many ways in which it can do. I just list them down and then talk of them one by one. So the first way is by what is called as clock rate, right? Okay, the second one is called as instruction execution rate, right? Okay. The third one is called as a spec rating. And the fourth one is called as an Amdahl's law. So So what are we saying? Our intention is to somehow quantify the performance of the computer. Again, this is not a very exhaustive thing in the sense that I could have asked you different difficult questions like what would you look for when you go and buy a machine. So somebody could say, I would look at the RAM speed and no, I would look at this and I would look at the cache and so on. Well, all those things define or in a way characterize the performance, right? But we are trying to keep it still simpler because we haven't yet seen all the aspects of a computer, so we really don't know, right? So we will try to see them one by one and see what it means. So let us look at the first one. Well, clock speed is fine. Clock speed is fine. So whenever you go to the market, you ask that person, what is the processor? So he says some number. He says, no, Intel i5 8th generation or something like that. Well, that number doesn't really ring a bell. Then you ask him what is the processor speed, and he says so many gigahertz. So suppose he says 2 gigahertz, and then you go to the next shop. Somebody says 2.5 gigahertz. You know that this fellow has a better processor, right? So the clock speed is fine, right? But clock speed is fine assuming the same ISA, right? What do we mean by this? It means that if somebody has two different processors and both the processors have the same architecture, then a processor which has a higher speed is certainly faster, right? A processor which has a higher speed is certainly faster. But if you have two different processors with different architectures, which means you really don't know what is there, talk about how operations is it broken down into, and so on. So for one instruction, do you do 100 atomic operations or just 5 and so on? So different ISAs will have different things. So if there are two different ISAs, then clock speed is inconclusive, right? So the comparison is inconclusive, which means clocks, just by knowing clock speed, you just cannot figure out which is faster. So what do? We move on to the second one. We say that if your say executes faster, it is fast, which seems fair enough. So what we are saying is that if somehow you could time your execution time, so you could figure out the time it takes to execute your ISA level program, then things could be fine. Which, well, it seems so. So let us try doing this one. So what do we want? Implies calculate execution time of program. And in this course, whenever I say a program, it will always be an ISA level program unless I say otherwise, right? So in this course, particularly for this course, so for example, you do a C programming course. So whenever the teacher says write a program, he's referring to a C program. Similarly, when you talk of architecture, whenever I am talking of a program, I always mean an ISA level program. So I might not say that all the time, but so essentially, I want to calculate the execution time of a program, right? Okay, so what I will do is I will define, so I will have certain assumptions or definitions, and then we will go ahead to do that. Right, so we assume a clock, right? We assume a clock whose frequency is F, and whose frequency is F, and cycle time, this is F, right? Cycle time tau is 1 by F, right? So we assume that there is a clock with a cycle time of this. Okay, what is the other assumption that I do? I assume that, okay, my ISA level program has I instructions instruction types has I different instruction types, right? And IC is the number of instructions, right? Okay, IC is the number of instructions. Okay. So, okay. And we assume okay, so what are we saying? That you have an ISA level program, it has I different instruction types, and totally there are IC number of instructions. So if I talk of a particular type, uh, sorry, each ISA level program has n instruction types. Sorry, my mistake. No, n different instruction types, and if I look at a particular type II, right? Then it has a CPI of CPI subscript I, where CPI refers to cycle per instruction time to execute. And again, whenever I say cycles, it will always mean processor cycles, right? So otherwise, I will specify explicitly, which cycles I am referring to. So it refers to processor cycles, right? So okay, so if you understand this, I can derive something called, so I know the CPI of every instruction, right? I know the CPI for every instruction. So I can derive something called as average CPI for, so I can derive an average value of CPI, right? So it is called average CPI. So let us call it as CPI, just as CPI. So I can write this as summation I equals 1 to n CPI I into II, right? And this, execution time of program, right, which is T. This can be written as IC into CPI into tau, because tau is the time it takes to execute one cycle. So these number of cycles will execute in so much time, and this is per instruction. So if I multiply by the number of instructions, I will get the time it takes to execute my IC level program, right? Okay, I just want to write one more thing. If you remember, a little while back, I also said, right, I just know where did I say that? Yeah, I said it here, right? So some instructions require both processor cycles and memory cycles, right? So, okay, so what I can do is, I can write, so I can do some more assumptions. So I can say assume each instruction requires, what does it require? It requires P number of, okay, P number of processor cycles, right? M number of memory cycles, and K is the ratio of memory cycle by processor cycle. What this means is that an example could be example K is equal to 10, means memory is 10 times slower than processor bus. So memory bus is 10 times slower than processor bus, right? Or memory is slower than 10 times processor bus, right? So,
Excuse me, sir.
yeah, I think the time is we are through with time, right?
Yes, sir.
Yeah, I know. But I'll just write one more equation and I'll stop. Right. So if I know this, I can take this equation number 1. Right. I will rewrite this equation number 1. So I rewrite equation 1, and how do I write it as? T equals, right, IC into, right? And if you observe, this cycles per instruction was referring to processor cycles. So this is quantified in terms of processor cycles. But now what I'm trying to say is an instruction, an average instruction has P number of processor cycles and M number of memory cycles. So can somebody tell me what would be the value of this CPI? Can somebody tell me in the chat what would be the value of this? If I want to write all this in terms of processor cycles. Anybody? See, up till now, I was assuming an instruction only requires processor cycles. But now I'm saying I know an instruction requires, yes. So somebody knows that. Who is that? Pulkit. Very good, very good. So he says P plus M into K, and this would be tau. Right? It depends on the assumption, right? So up till this, my assumption was that an instruction only requires processor cycles. But if I say assuming an instruction requires P number of processor cycles, M number of memory cycles, you try to express this thing in terms of processor cycles. So this becomes P plus M into K. And this is also called as the performance equation, and it has 5 performance parameters. So what will I do is yeah. Okay. So what will I do is still have some interviews lined up. So I will stop, right? So okay. So any questions till now? I can take it. Otherwise, I will take the questions in the next class, and we will continue from this point onwards. So I will tell you how these parameters are influenced and how you can use these parameters to quantify the performance of an architecture. Right? So any questions here? I can take it. Any questions? I can take it. Otherwise, I'll stop.
Sir, in the summation formula, what is II, which you have multiplied with CPI?
Yeah. So I is instruction type, right? Instruction type. So okay. So maybe in the next class I can do an example. So I'll just give you an example. Just assume an abstract architecture which has 3 types of instructions. One are arithmetic instructions. The other are say branching instructions, and the third are memory instructions. Right? So these would form 3 different classes, right? So I would refer to the class of the instruction, right? So whenever I take an instruction, I could say whether it belongs to class 1 or class 2 or class 3. Does it
But sir,
answer?
what does multiplication means in that? Because II should be a number, right? In the summation formula, CPI average that we are taking.
Okay. 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 I get your point. So okay. I get your point. So I'm not writing it down, but you can write it down. So I is the count of the number of instructions of type I. Can you write that? Is that fine? Are you able to hear?
Yes, sir.
Right. So II is
Yes,
the
sir.
count of the number of instructions of type I. Right. So you can write that down. Maybe in the next class I will take an example also to calculate how that happens. Right. So that's fine. So can I stop now? Can I stop? So Darshan says it is a number of times specific instruction used. Yes, it is the count of the number of instructions of type I. So CR, can I stop?
Yes, yes.